All right. All right. Good evening, everyone, and welcome to week 8 problem solving sessions of conduction and convection heat transfer. And for last couple of weeks, I think we were studying about convection. We completed our study on conduction, and then we started studying about convection. And the last week were mostly derivation of various equations. Like we have reviewed the fluid mechanics, mass, momentum, and energy conservation. We have derived it. And if you see what we did this week, we also continued that derivation and applied it to a case uh, like a heated flat plate, right? So when there is a flow over a heated flat plate, how will you perform a convection analysis is what we did. So basically a boundary layer theory for flow over a flat plate is what we apply. We already studied that in fluid mechanics. Here, in addition to fluid mechanics, we also solve the energy equation, because energy equation is going to tell us the heat flux, right? So we at the end of the day we are interested in heat flux or Nusselt number. So that we in fact derived it, and we obtained the relation of Nusselt number by solving these equations. So whatever we solved in last week 7 and week 8, is something we applied it, and then we got the heat flux from the boundary layer, from the flat plate, right? What is the heat flux that we can that is being advected, or that is being convected by the flow over a flat plate. So that is what we did. It's just to give you an understanding of what is happening. Okay. Um, so maybe we will quickly go through notes once. So the reason is, in week 8 we mostly did the derivation, and I guess I've gone through the assignment problems, and it should be fairly easy if you understand what is happening. I mean, if you understand these derivations, and if you understand the final relations, how this works. Okay. It is not very big problems. They are not very big problems. Like just to test your understanding. A simple questions have been asked in the assignment. And I certainly think that if I go through once the equations, a quick recap of the equations, and to give you a big picture, it would be helpful for you. So that we are going to do now. And after we finish that part, I will solve two questions. Okay. It's also a simple question, similar to what you see in your assignments. We will solve these two questions, and if you have any doubts, maybe I can take it at the end of this session. So probably I think we don't have any audience today, and I think everyone is going to watch my YouTube video. That's all right. So if you find any problems in understanding whatever I'm going to teach today, if you find any problems in understanding these derivations, please let me know. You already have my email, and also you have you can always come the next week, and then I will be able to resolve your doubts. So basically I'll be solving problems just for first 1 hour or 1 hour 20 minutes, and remaining 40 minutes to 1 hour is for you to ask any questions if you have any. Okay. So feel free to join the next class. Also, if you want, you can also drop me an email. I will be happy to respond. Okay. All right. Now let's quickly go through the derivations. As I said, so we started convection. And we initially thought in this way, like there is a flat plate and the flow is going, and now if you want the heat flux, so basically it's just an energy balance across the interface. If you balance the heat flux, conductive heat flux to the convective heat flux, and then if you simplify this, you will be able to get a Nusselt number correlation, and a Nusselt number will depend on certain values, and these values, how these values are going to affect, we had a fairly small idea, a little bit idea, and this become more and more clear once we solved all the equations, right? So initially we started with Reynolds transport theorem, and this is like basic general theorem for any transport quantity, for example mass, momentum, energy, and also species concentration, electrical charges, any transport quantity, any quantity that is getting transported will follow Reynolds transport theorem. It's basically simplest theorem, or fundamental theorem. This Reynolds transport theorem, once you derive this equation, you can just change this property n. Extensive property is capital N and intensive property is small n. You can just play with this property to get different conservation equations. So initially, we derived the conservation of mass. We made some certain assumptions which is good for this subject at least, and we derived the continuity equation. And then what we did, we carried out the momentum conservation equation. Basically n is momentum and small n is velocity. It's a specific quantity of momentum, and we derived the momentum conservation equation. For example, we have this external force acting on the system, and this force is actually can be divided into surface and the volume forces or body forces. And to find the surface forces, we need traction vector. And what we did, we derived the traction vector, we mapped the stress tensor to the traction vector, and then we were able to uh, get this relation. And then we applied angular momentum and showed that this stress tensor is basically symmetric. Okay, and once you found out the traction vector in terms of stress tensor, you substitute that in the momentum equation, and you end up having this Navier equation. It's not a Navier-Stokes equation, it's just Navier equation. And then you apply Stokes law as approximation here, then it becomes a Navier-Stokes equation. So for example, in this equation, this is a momentum equation, a general equation. Only thing is the unknowns are density, velocity. In addition, we also don't know the shear stress, or this is a stress. This is also, we don't know the stress tensors. Basically this is a tensor, so you will be having 9 components, but since it's symmetric, you will have 6 components. So there is additional 6 unknowns. So we need something to close this equation. So we have what you call the constitutive relations, and for that we decompose the stress tensor into hydrostatic and deviatoric. And deviatoric, we know it is going to be rate of deformation tensor, and then we did certain calculations. We introduced this CIJKL, a 4th order tensor, and then we reduced that into by assuming it's an homogeneous and isentropic scalar, we reduced it into, from 81 we reduced to 3, and then from 3 we reduce that into 2. And once you get that, you end up having these two unknowns are nothing but your viscosity and volumetric dilatation coefficients. And once you have these, you can actually express the stress in terms of a hydrostatic and deviatoric containing 2 components. One is based on viscosity and the other is volumetric dilatation coefficient. And then we applied Stokes hypothesis, telling that mechanical pressure is a thermodynamic pressure, and hence we were able to simplify that 2 unknowns to 1 unknown, which is just becomes a viscosity, which becomes a property which we already know. So it is no more unknown. So basically what we did is we had 6 unknowns initially when we started the stress tensor. Now we reduced that, we express the stress tensor in terms of velocity gradients and the known property viscosity. Okay, and that is how we got this Navier-Stokes equation. And these are the assumptions. These all we already know from the last week. And what we found out is that we need to know, we had this additional unknown pressure. So in order to close the pressure, we need to have an equation of state, and the equation of state again introduce an additional unknown called temperature, and we need a equation to solve for temperature, and that is what the energy equation is. Again, you go back to Reynolds transport theorem, you write the property to be total energy and the specific property to be specific energy, right? Capital E and small e. And then you apply first law of thermodynamics, which is delta E is equal to Q minus W. And then W is again because of surface force and the body force. So surface force is we express this in terms of stress tensor. Initially we expressed in traction vector, and traction vector we change to stress tensor, and once you perform all this math, you will end up having this energy equation. In this Q is nothing but your heat generation and the heat flux vector. Okay. Alright, so finally you will end up having this internal energy form of energy equation. In fact, actually you will end up having this total energy equation, and you want temperature, which you can obtain from internal energy. So we try to read this total energy contains only internal energy and kinetic energy. So to get kinetic energy, we take the momentum equation dot product with the velocity. You will end up having mechanical energy equation. You subtract the mechanical energy equation to the total energy equation. You will end up having internal energy equation. Okay, this is where I think we stop. We also quickly gone through this term tau ij dou u I by dou xj, which is nothing but your viscous dissipation term, and we also prove that it's always positive. And so which means because of viscosity of the fluid, when the fluid flows, the viscosity, because of rubbing motion between the fluid surface, it's going to generate heat, and the heat is going to contribute to the internal energy. It's going to heat it, so it will always be positive. It cannot cool it. Okay, that is what when if it is positive, which means the left hand side of this equation is positive, which means the internal energy will continuously increase. If internal energy increases, temperature increases. Basically it's a heating process. So this is what we summarized in the previous week with a viscous dissipation term. Now what we went forward is from this what do you call the internal energy term. Since internal energy is something we don't measure, we measure temperature, and temperature is what is important for us. So what we try to do is change this internal energy form into temperature form. For that, first we express the internal energy in terms of enthalpy, and then you simplify it. You can express this energy equation in terms of enthalpy. Only thing is, additionally you will have dp by dt term. Okay, and so and then you express the enthalpy in terms of temperature. We all know enthalpy is a function of both temperature and pressure. For ideal gases, it's just a function of temperature, but here we are dealing with any substance, simple compressible pure substance with no phase change, right? So we have to take that pressure also into account, and hence you can simplify this, use Maxwell equation, compare the terms, all these things we already, I think we studied in week 2 or 3, I guess. And finally you will end up having this temperature version of energy equation. Okay, so basically we actually kind of derived this in our during conduction itself, but in conduction what we assumed is the energy stored is something like there is no velocity, right? There is no flow in it. Here you would certainly have flow in it. Okay, so this capital D by dt is the total derivative. So if you expand this, you will have velocity times dou t by dou x, and u times dou t by dou x, and v times dou t by dou y. So that is the convection part of the equation, or the advection part of the temperature, and this is the energy equation for in temperature form. Okay? And also it is in non-conservative form. So why do we say non-conservative is this temperature is not a conserved quantity. For example, mass is a conserved quantity, momentum is a conserved quantity. Okay, you will conserve the momentum. Similarly, you will conserve only energy, but you don't conserve temperature. Temperature is not conserved. Okay? So that's why when you express this equation in terms of energy, it is called a conservative form of energy equation. When you express this equation in terms of temperature, it becomes a non-conservative form of energy equation. Okay, that's why we use these. Okay, and then we applied heat flux vector. We are going to use Fourier's law of heat conduction, and then we will end up having this equation. So this is we derived in the first half of this week, and then we carried forward. Okay, so we derived energy equation. So this actually closes our system. If you think back, we started with Reynolds transport, and we derived mass momentum equation, and we found out that there's additional pressure. So in order to find the pressure, the density, there is 3 velocity and additional pressure you had. So 5 unknowns, but you have only 4 equations. 3 momentum and 1 mass conservation. So you need one more additional equation, so you added equation of state. And what equation of state did? It added temperature also in it. So you need additional energy equation. And this is what the energy equation is. This doesn't introduce any more unknowns. So P is something, it's already we taken it to be unknown. And temperature. So these are, so mass, momentum and energy. These three are coupled partial differential equations which you need to solve for any convection problems uh, to find your quantities of interest. Okay. Uh, so that is this. So by deriving this, we actually concluded that these are the equations we require to solve a convection equation. Now, I mean to solve a convection problem. Now, what we are trying to do is, let's say I have derived this, I have to apply it for certain process, and I have to get, uh, let's say, heat flux. Heat flux is my area of interest or the quantity of interest. What is the heat flux I can get? So that certain application is this thermal boundary layer development over a flat plate. So we know that there will be a boundary layer development because of no slip boundary condition at the surface, hydrodynamic boundary layers. So when the flow is like this, it is going to see the surface. Surface will be at velocity. Surface is rest, or it can move in some certain velocity, but here the surface is at rest. So the fluid adjacent to it will also be at rest. So it has to come to rest. So that's the no slip condition. So if you make that rest, then it starts pulling the upper layers of the fluid, and because of viscosity the momentum diffusion happens. That is what you are seeing here, boundary layer development. Okay. Similarly, what you also have is when there is a temperature gradient, when you have a T wall to be at some certain higher temperature than the T infinity, so you will start having this kind of temperature profile, and you will start having development of the thermal boundary layer. Okay. Now the process that is going to take care of this is your heat conduction. Okay. So basically you have this heat conduction coming over here, which is some are taken by the convection, so it gets cooled a little bit here, and then remaining it gets propagated. Okay. So basically the diffusion happening, the heat diffusion happens along this direction, which makes the similar to momentum diffusion you have here. Here you have heat diffusion. Okay. So this is how your thermal boundary layer develops, and as I said, we related this thermal boundary layer, hydrodynamic boundary layer thickness with the diffusion coefficient. Here it is kinematic viscosity. Similarly, we can also relate the thermal boundary layer thickness to the thermal diffusivity, okay, which is alpha. And so del by delta T will be mu by alpha, and mu by alpha is nothing but your Prandtl number. So there is some relation between del by delta T, delta by delta T with Prandtl number, and that is something we even derived it and we showed it what is the relation. Okay. And then we have we wrote down all the equations, right? For boundary layer, the equation simplifies as this, so you should not get confused. This is still this equation, but since it's a boundary layer, it's a 2D steady. All these approximation we made, incompressible, all the approximation if you make to this equation, okay, you will end up having this equation. Okay, this is not something new equation we just introduced, we already derived it. And then this equation we further simplified, and then we applied thermal boundary layer. To be applicable, we need to have, this is some additional, if you remember the boundary layer theory, we used to do this, right? Delta will be the thermal or hydrodynamic boundary layer thickness is very much smaller than the length scale along the x direction, right? Similarly, we are going to do the same approximation, like thermal boundary layer is very much smaller than length scale. Okay. When you do this, you will end up, and then you compare the scales, same thing that you have gone through the boundary layer. So if you haven't if you are not sure about, if you don't remember your boundary layer equations, if you haven't studied in your fluid dynamics course, I recommend you to watch Professor Suman Chakraborty's fluid dynamics videos, where he derives boundary layer velocity boundary layer equations. Okay, velocity boundary layer equations and their uh, solutions for the same flat plate. And we are actually using those solution whatever he derived in thermal boundary layer. Okay, so if you're not familiar with it, I strongly advise you to go through those lectures. I think it's in fluid mechanics course. So you would be able to access it in YouTube. Should be you that should be straightforward. All right. So yeah. So finally, we had this. These are the velocity boundary layer equations. For example, in the fluid mechanics course, you would have used these two equations, and you would have derived the expression for hydrodynamic boundary layer thickness. Now, in addition to this equation, we also have energy equation, and then we it looks like similar, but we also need boundary conditions to be similar. So what we did non-dimensionalization, and we end up having a similar equation, and we applied something called Reynolds analogy. That is what Reynolds did basically. This is not something we did, it's Reynolds did. And he applied this analogy, and he said that whatever the, since governing equation boundary conditions are same, whatever the expression that you derived for the hydrodynamic boundary layers is applicable for theta. Okay, so it's just mathematics. Okay, so if that is the case, then but for this to happen, you need to have Prandtl number to be 1. Okay, if that is the case, then if we find the heat flux vector, so it is going to be uh, so the shear stress uh, on the wall is same as the heat flux on the wall. Okay, that's basically the analogy between these two. So when you do this equation and you equate these two, you will end up having skin friction coefficient to be nothing but Nusselt number by Reynolds number by Prandtl number. But Prandtl number is 1 for this assumption to be valid. In fact, we actually derive it to be Cf by 2 is Nusselt number by Reynolds number. But you can add Prandtl number because the assumption is Prandtl number is 1 for this. So this is how the equation looks. So this is replaced by Stanton number, and hence you can write Stanton number to be Cf by 2. Okay, so Stanton number is nothing but convective flux divided by axial advective flux. Okay, so so basically the fluid is flowing, and while flowing it is also taking some heat. So the actual advective flux is also taking some heat, which becomes the convective flux. Okay, this part is the advective flux, which just tells that this much amount of fluid is flowing. Okay, and the convective flux is, while it is flowing, this much amount of heat it is carrying away. That is the convective flux. Convective flux is nothing but heat transfer due to advection. Okay, that is the convective flux by axial advective flux, and that is Stanton number. Stanton number is Cf by 2. Okay, so these are the assumptions we made, and now we know. So if Prandtl number is very much less than 1, it's so as we said, Prandtl number is nothing but del by delta t. If Prandtl number is very much less than 1, then delta is very much less than delta t. Similarly, the otherwise vice versa. So now you have this thermal boundary layer equation. So based on order of magnitude analysis, you try to get an order of magnitude for this thermal boundary layer thickness, and that comes out to be del by delta t is equal to Prandtl number per half. Okay, so it's just order of magnitude. You just need to select a proper scale, uh, and if you equate the LHS and RHS of the equation, you will end up having this relation. Okay, and you know, as I said, we are interested in the heat flux at the wall, and non-dimensional form is nothing but temperature gradient at the wall, and temperature gradient at the wall, non-dimensional temperature gradient at the wall is nothing but your Nusselt number. So this Nusselt number we try to calculate from here. It will end up having Reynolds number power half and Prandtl number. It goes as, okay. So you should note this. This Nusselt number is going to be it. It's going to be a function of Reynolds number power half and Prandtl number power half. We still don't know how what is the exact relation. Okay? The exact relation we will know while we solve the equation based on the momentum integral theorem, right? So this is for Prandtl number very much less than 1, and the example is liquid metals, and when Prandtl number is greater than 1 you do similar analysis, and then you will end up having this relation. Okay? And here the difference between these two is the Prandtl number is having 1 by 2 in, sorry, the Nusselt number is related to Prandtl number power half. If Prandtl number is very much less than 1, Prandtl number is very much greater than 1, it's going to be 1/3. That's the difference. Now the exact relation is we can obtain from the integral method of thermal boundary layer. We already did this for momentum boundary layer. We are going to just apply it for thermal boundary layer. So it's nothing but you integrate the entire boundary layer uh, from 0 to delta T. You integrate the entire equation across the boundary layer, and that will give you the heat flux. So that is what we are directly getting it. Okay. All right. So there's a lot of mathematics, and you can perform this analysis. And finally, you will have this in energy integral equation. And now, you non-dimensionalize it, and you will end up having same integral energy equation in a non-dimensional. And then first case is Prandtl number is very much less than 1, and for that we take theta to be in this form. This is something we also took that uh, in momentum boundary layer theory. So if you you can recall the boundary layer relations that we derived for momentum equation, we actually express this in terms of third order polynomial, and then we try to get the hydrodynamic boundary layer thickness. So we are doing a similar exercise for the thermal boundary layer thickness. Now you assume this is a rough profile of your temperature inside the boundary layer, and if you substitute in this equation, so this part is nothing but your dimensional temperature gradient, which is something you want. And so you substitute here and you end up having delta T, and then you apply boundary conditions and you end up having delta T by x square is nothing but 8 times Reynolds number per Prandtl number. So basically you can see that delta T by x is nothing but Reynolds number power minus half, Prandtl number power minus half. This is for Prandtl number very much less than 1. Okay. Now if you define Nusselt number to be, this is the definition of Nusselt number, nothing but hx by k, and now you substitute whatever we found from here and here, you will end up having the exact relation of Nusselt number. That's how the Nusselt number is varying with x, which is 3 by 2 root 8 re power half and pr power half. Okay, now this is a local Nusselt number, so you can find the average Nusselt number, you can find the average convective heat transfer coefficient by just interpreting it. Alright, similar analysis we can again perform for Prandtl number very much greater than 1, but only thing is we have to take the velocity profile also into consideration, because your thermal boundary layer thickness is going to be very much high than the momentum boundary layer. So your entire momentum boundary layer is going to be within the thermal boundary layer, and hence the velocity inside your thermal boundary layer is going to have your momentum boundary layer and then u infinity throughout, right? So you should have the entire uh, relation of velocity inside the thermal boundary layer, so you have to use them in your boundary layer equations. That is the change we have. So and then you simplify a lot of algebra here, and then if you recall, this is what we derived in the momentum integral equation. So this is something you can watch this fluid mechanics lecture of Professor to understand how this really root of 280 by 13 came. Okay. All right. And then you simplify it, and I think professor stopped here. Multiply both sides by z of x, and you will end up having the relation. So I carried on, but I'm not going to show you. You also carry on, and you will end up having Nusselt number to be 0.331 Reynolds number per half and Prandtl number. Okay. So you perform this homework exercise, whatever professor said. Um, so the exact relation, so this is something we got it from the order of magnitude analysis, but only thing is we didn't know what is this constant. Similar, same goes here also. Uh, we didn't know what is this constant in the order of magnitude analysis, but it gave us how the magnitudes depend on each other. Okay. So that is what uh, we did in the class, and I hope these derivations are clear for you guys, and if you have any doubts please feel free to ask me. And yeah, I guess 3 more people join, so if you have any doubts regarding the derivation, you can ask me. I would be happy to help you out. If not, we will go forward and solve 2 questions. It's a simple question. uh, Hopefully that will be helpful for your assignment. Thank you, Mustafa, Manoj, and Avinash Shivam for joining. So I hope there is no problem with the derivations that Professor solved. If you have any problems, please let me know.
Sir,
Yes, yes, please go
sir,
ahead.
I'm Mustafa. I'm Mustafa.
Yes.
Sir, the flow work and pressure work both are the same.
Flow over.
Flow work and pressure work.
Can you come again? Flow over airfoil.
Flow work and pressure work.
Oh, flow work and pressure work. Okay.
Mm.
Um, See, so there are only 2 kinds of work. Okay.
Mm.
One is, so because of surface forces, and one is because of body forces. So now, if you
Okay,
have
sir.
to see, you have to think, what is this surface force? Is the surface force occurring because of a flow? If it is yes, then it becomes a flow work. Okay. So you have the surface forces, but that is actually stress tensor. Now, uh, that stress tensor is going to give you pressure. Okay.
Okay, sir.
So
Okay, sir.
in practically you can say that flow work is same as the pressure work. Okay. That is how we derived the equation, right? You understand my point?
That's mean dt by dp by dt we can say as flow work.
Uh, dp, see, it's a work, right? Dp by dt,
Can we say flow
yeah,
work
we
as a
can
flow
we
work?
can say it's a flow work, but that is a flow work in the uh, enthalpy equation. Okay, so dp by
Okay,
dt
yes.
in general it's not a flow work. Pdv work is the pressure work. Okay, that you can say as a flow work. That is not a
So,
problem. Okay.
that is dp by dt is we can say flow work.
So pdv is what I'm talking. So this is the total energy equation, right?
In the derivation, the last
Ah,
time I'm asking about.
so this is the total energy equation. You have this stress term. This stress term will give rise to, for example, in the internal energy equation, you have this viscous dissipation, and also you have this viscous dissipation is nothing. I'm sorry. I mean, this stress term will lead to 2 things. One is viscous dissipation. The other is pressure work. Okay? So this is what. So these are coming from the stress tensor. So this is what the flow work is.
Okay, sir.
Okay. So it's just a terminology. I mean, usually you just say pressure work. Pressure work explains everything. PDV is the pressure work
Okay, sir.
or work done by pressure. Okay. Also, you can also think in this term. Pressure is what is driving the flow. If whatever the pressure work is done, is what the flow. Okay. All right. Interesting.
Yes, sir.
Any other questions?
That is pressure work is tending to flow. So
Pressure work is dP by dt. Sorry,
okay.
sorry. Pressure work is PdV. PdV work is what work done due to pressure. That is pressure work. Okay.
That's why flow is happening.
Right, right.
Why this the we can say DP by DT is
See,
can we say flow work?
yeah, we can say it's a flow work. That is fine.
Okay. Okay.
See, the PdV is pressure times. So you can see that P into divergence of V, right?
Okay, sir.
The divergence of V represents the flow. So you can say PdV work is nothing but your pressure work, which is also flow work. You're right.
Okay, sir. Okay, sir. Okay, sir. Madam asking DP by DT, not PDV.
So dP by dt, that's what I'm trying to say. dP by dt has lot of things in it. dP by dt has dou p by dou t, and uh, additionally there is a u times dou p by dou x, right? So that does
Okay.
not really represent the flow work. If you ask
Okay.
me, it's in enthalpy equation. The flow work is within it. I would not directly associate dP by dt to flow work.
Okay, sir.
Okay, you understand? Only the
Okay.
P times divergence of V is the exact flow work.
Okay, sir.
dP by dt is just the manifestation coming because we express the energy equation in terms of enthalpy.
Okay, sir.
Okay, so if you see the derivation, I would not call dP by dt flow work. That's what I'm trying to say.
Okay, sir.
You,
Okay, sir. Thank you, sir. Thank you, sir. Clear.
okay. Let me just quickly show. See, this P by rho is what is causing that, and this is what is causing dou p by dou t, and this dou p by dou t is within dP by dt. So I would not call this pressure work or flow work dP by dt. Okay, all right.
Okay, sir.
Any other questions?
Clear.
Okay, if there are no more questions, I will move forward and solve these two questions. These two questions are a little bit similar. It's also very easy. You guys are going to tell me answer. So this is a flat plate boundary layer equation for force convection, which are given as follows. So this is the mass conservation, this is the energy conservation. We can also write a momentum conservation. We know that x is in axial direction, y is in transverse direction, and other symbols have their usual meanings. Okay. Now the dependence of Nusselt number on Reynolds number can be determined by order of magnitude analysis, which we already did. So for a low Prandtl number fluid, answer the following questions. So low Prandtl number fluid means in the limit of Prandtl number very much less than 1. Okay. So what they're asking is what is the dependence of Nusselt number on Reynolds number and Prandtl number. Right? We already know this. We derived it. I will just write that here. Nusselt number is nothing but Reynolds number power of Prandtl number power. This is at Prandtl number very much less than 1, right? This is our dependence, that is what we derived it. So what they are asking now is if the fluid viscosity is doubled, keeping all the parameters same, how does Nusselt number changes? So if we now let's say I have mu1 is my initial viscosity. Now I am changing the fluid viscosity, okay, and that is nothing but 2 times the mu1. Okay, now the fluid viscosity is doubled. Now what happens to Nusselt number? What they are asking. So initially I had Nu1. Now what is going to be Nu2? How it is going to be related to Nu1 is what they are asking. Okay. So for that what we will do? We can express Nusselt number in terms of Reynolds number and Prandtl number, and we can also, so this is a viscosity, right? So we can express Reynolds number and Prandtl number in terms of viscosity. So how will you write? You will write U infinity L by nu power of, this is your Reynolds number, and Prandtl number is nu by alpha cutoff, right? Now you can simplify this further. Nu infinity L by nu times nu by alpha power of nu gets cancelled, so this goes as u infinity L by alpha. Alpha is k by rho Cp, is nothing but u infinity L by k into rho Cp. Now they are asking, if I double the viscosity, how is my Nusselt number changing? So nu1, so how it is going to change? So this Nusselt number doesn't depend on your viscosity at all, right? There is no viscosity term. Although we had Reynolds number and Prandtl number, it automatically gets adjusted if you change only viscosity, right? So this relation actually gives us that the nu1 will be equal to nu2, because both of them doesn't depend on viscosity. Depend on viscosity. So whether you change the viscosity or not, it's not going to change. It remains the same. Okay. Remember, this is one Prandtl number very much less than 1. Okay. Hello, can you hear me? Mic isn't working. Hello. Hello. I guess I am back now. I think there was some problem with my mic. Were you guys able to hear me? No?
I'm able. Yes, sir.
Okay. Thank you, Mr. All right. So, so basically, what I'm trying to say here is, let me check my recording. So basically, what I'm trying to say here is, when you simplify this Nusselt number relation, you will the viscosity cancels out. So whatever the viscosity change you will do, it does not affect the Nusselt number. So that is going to remain same if you just change the viscosity. Okay. Now the second question that they are asking is, if the fluid density and thermal conductivity both are doubled. Okay. Let's go back. Then what happens to Nusselt number? Let's write the Nusselt number relation. So it's going to be, we already derived it, right? U infinity L by K into rho Cp. So what they are telling, rho is also doubled. Thermal conductivity both are doubled. So rho 2 is nothing but 2 times rho 1. And thermal conductivity K2 is nothing but 2 times K1. Okay. So you can write Nu1 by, Nu1 is U infinity L by K, K1 rho 1 Cp, and Nu2 is U infinity L by 2K1 2 rho 1 by Cp. So this actually gives Nu1. So this also again says that remains same. The Nusselt number does not change. But if you change one of them, it is going to change. Okay. Okay, wait. I think this has to be power 1 by 2. Whole power 1 by 2. Okay. So these are simple thing. I'm just showing it to you so that it will be clear. Now the third question is, if the fluid density and heat capacity both are doubled, keeping all the parameters same, how does Nusselt number change? Fluid density and heat capacity. Previously it was fluid density and thermal conductivity. So what I'm going to say now is fluid density and heat capacity. Cp2 is 2 times Cp1. So again, let's say we will write the correlation. It will be U infinity L by K into rho 1 Cp1, and nu2 is U infinity L by K into rho 2 Cp2, where rho 2 is nothing but 2 times rho 1 times Cp1 whole power 1 by 2. Okay, so this actually gives 4 times nu1, 4 power 1 by 2 times nu1, which is nothing but 2 times nu1. Okay, so basically your Nusselt number is doubled. So you can also think in these terms. When you change the density, you are having uh, more fluid going through, and when you change the heat capacity, then the capacity of the fluid to take the heat from the wall is also increasing. So if you just change the density, it is going to increase your Nusselt number. If you change the uh, Cp, it is going to further more increase it. That's why we have 2 times the Nusselt. Okay? The same doesn't go with fluid density and thermal conductivity. Okay? All right. I hope this is very clear, very simpler. Now let's solve the second question. Okay. The second question is same thing. I'm not changing anything. The same equations. Only thing is I'm asking for a higher Prandtl number. So higher Prandtl number means Prandtl number very much greater than 1. And we know what is the dependence of Nusselt number on Reynolds number and Prandtl number. What is that going to be? NUX is going to be Reynolds number power half and Prandtl number power 1 by 3. So you have to be very careful whether it's a low Reynolds number or high Reynolds number. Based on that, your relation changes. Okay. Now, second question that they are asking is, if the thermal conductivity of fluid is increased by a factor of 8, how would the Nusselt number change? So the same expression we are going to, so probably we will simplify this in terms of properties. Nusselt number is nothing but rho, uh, so Reynolds number is nothing but U infinity L by nu power half. Prandtl number is nothing but nu by alpha power 1 by 3, right? And you want to write in terms of nu is there. I want to write alpha in terms of K and rho Cp. So what would I do? U infinity L by nu power half and nu by K rho Cp power 1 by. This is your Nusselt number dependence on all the parameters and properties. Now I am telling I'm going to change the thermal conductivity of the fluid by the factor of 8. Okay, so basically you can write it as K1 and K2. K2 is nothing but 8 times K1. Okay, so the reason I gave 8 is it's easy for doing taking square root and cube roots. Nusselt number nothing but Nusselt number, let's say 2, nothing but U infinity L nu, all these are not changing, half into mu by K is 8 times K1, so you can write this 8 times K1. So this is nothing but you can write it as Nu1 divided by 8 power 1 by 3. This is nothing but Nu1 by 2. Okay. So which means when you increase the thermal conductivity your by 8 times, then your Nusselt number reduces by half. Okay. All right. So This is a little bit counterintuitive if you think about it. Why would a thermal conductivity have a bad influence on heat transfer? But I'm not going to give you answer right now. You think about it. Uh, why increasing thermal conductivity is going to reduce the Nusselt number. If the Nusselt number reduces, what happens? Your heat transfer coefficient reduces, right? Convective heat transfer coefficient reduces. So basically, Nu is equal to Hx by K. Okay, H is nothing but Nu K by X. Although K increases by 8 times, Nu reduces by half. Okay. Okay. So in general, heat transfer coefficient is increasing. So heat transfer coefficient from H1 is greater than H2 because of thermal conductivity effect separately. But if you think in terms of Nusselt number is reducing. Okay. So I will let you guys reason that out. Although heat transfer coefficient increases, Nusselt number reduces. Okay. Something food for thought. Now the third question, if the fluid heat capacity and thermal conductivity both are increased by factor of 8. So we are adding two more things. Now initially we increased thermal conductivity, now we are increasing capacity also. By now you guys must have guessed. So it's going to nullify this effect. So U infinity L by mu power of, so mu times 8 K1 rho 8 Cp. So 8 gets cancelled. So that is going to same as Nu1. So which means this is also remains same. Okay. So now, even though Nusselt number remains same, because thermal conductivity has changed, your convective heat transfer coefficient is going to increase. Okay. So Nusselt number remaining same doesn't mean that heat transfer coefficient is remaining same. Okay. Some word of caution. All right. Now the final part is, if the kinematic viscosity is increased by factor of 4 and the fluid density is reduced by factor of 4. Okay, one is increasing, the other is decreasing, keeping all the parameters same. How does the Nusselt number change? Let's calculate. What I'm trying is, kinematic viscosity is increasing by the factor of 4, is 4 times mu1, and what is the other one? Fluid density is reduced by factor of 4. Rho 2 is rho 1 by 4. Okay, let's substitute in the relation. Nux is U infinity L by nu by K rho Cp 1 by 3. Now Nu2 is, how would you write? U infinity L divided by 4 times nu1 power half times nu 4 times nu1 divided by K to rho 1 by 4 Cp over 1 by 3. Okay, this is also fairly easy, not bad. So you just remove this, then this becomes basically Nu1 divided by 4 power 1 by 2, which basically tells Nu1 divided by 2. So when you increase the viscosity but reduce the density, your Nusselt number actually decreases. It's going to be halved. Okay. So basically for this kinds of questions, I think you all are very good at solving. You just express Reynolds number and Prandtl number in terms of their flow properties and variables, and then you be a little bit careful because you have 1 by 2 and 1 by 3 everywhere. So if you perform this analysis, you will be able to tackle such problems straightforward. But try to physically correlate why would Nusselt number changes when you change viscosity, thermal conductivity and density. So you get that physical picture in your brain, then it will be much more easier. Although mathematically you will prove something, by reading the equation, this is increasing, this is decreasing. If that is the case, Nusselt number is expected to decrease or increase. You can get that feel, and then by performing this calculation, you can cross check your intuition. Understand that would be much better for you. Okay. Any questions you have till now? So I have these two questions for today. Uh, Probably in the next class we will solve a little more on internal flows. I think week 9 is about internal flows. In external flows, this is what we will be asking. So we won't be having any like correlations and all. Whatever we can derive in the board is what professor will teach, and that is what will be asked. Other things you can use it. The other things are other correlations that you see in textbooks are basically derived from experiments. So they do experiments. They have this order of magnitude analysis. This order of magnitude analysis tells that it depends on Reynolds number and Prandtl number in such a way. Now to find the constant number, it depends on a lot of things. So if you assume it's a laminar and whatever the assumptions that we made, then it becomes like 0.331 or square root of 280 by 13, all these whatever 3 by 2 root 8, right? All these numbers will come, but in reality that's not the case. It will be turbulent, it will be, till now we didn't talk about turbulent at all. So for turbulence you may need to solve additional equations, or you need to consider additional terms in the equation. Then only you will be able to solve this equation, and it becomes more complex. You add turbulence, it's a separate field of study. So what people do is, in reality, in all the experiments you will see turbulence, you will see all sorts of things, and underlying order of magnitude analysis tells that this is how this should depend on. So based on this, what they do, they parameterize and they just find the C1 from the experimental data. So what they try to fit this relation for an experimental data, and that is how they get different numbers as a constant, and that is why they are called correlations. Okay? It's not coming from the first principle. It's not coming from whatever we derived. We started from mass, momentum and energy, we derived it, we solved those equations, and then we ended up having some relations, right? But in the experiments that they won't do it. They do the experiments, they get the data, and they try to fit this expression, and then from that they get the constant. That's why it's called correlation. And those correlations we will not be dealing much in the textbooks. You can check the textbooks for learning more about this correlation, but it's just finding your proper problem. What is the problem that you're trying to solve, and finding an appropriate correlation from the literatures, from the previous experiment, and then solve your heat transfer. That is not really giving you that does not really give you much insights. Rather, this order of magnitude analysis gives you that. Okay? So that's why we will not go towards in discussing correlations. That is not of our interest, especially with this course. We will solve everything on the board, and we will try to explain it and give you insights on it. All right. So probably next week we will do internal flows. If you have any questions, you can stay back and ask. If not, we'll meet next week. Okay. I hope the derivations are clear, and if these are clear, I think you should be able to solve your assignment problem. All right. Thanks for attending, guys. We have Thanks for attending. If you have any questions, please stay back and ask. If not, we'll meet next week.
Am I audible, sir?
Yes, Manoj Kumar, go ahead.
Sir, the solution of assignment fifth week, na, sir. I think it is uploaded in week 6 also, sir. Solution only, sir. When I open that, sir, in week
Mm-hmm.
6, na, assignment solution. So it's showing same of fifth week, sir. Solution.
Oh,
I think PDF may be missing, sir, of sixth week solution, sir.
I see.
Just check.
Okay. Okay.
Lumped heat analysis problem, sir.
Mm-hmm.
So I think that one, sir, showing in 2 weeks, sir. Like just check, sir. In fifth and sixth week, sir.
Okay, six
Might be.
solution. Oh, okay. Same as assignment week.
Yes, sir.
So basically, you guys don't have week 6 solution then, is it?
Yeah, I think yes. Sir.
How about week 7, assignment 7?
That's okay, sir.
Assignment
Like
solution is correct?
yeah,
Okay. This
up to
is
fifth
not.
week I check, sir. Sixth week it is showing of fifth week solution,
Okay.
sir.
Okay. What I would do is I will ask professor about it, and
Okay, sir.
you can also raise this request in the common forum. Did you try to do that?
No, sir.
Okay, so what you do is, what I would request is you also raise this email in that
Yes, sir.
common forum, and then I will also anyway ask professor. In that way,
No.
it will be very quick. Okay.
Okay, sir. Thank you, sir.
Okay.